Okay, let's start. The exam is on Thursday, starts at 10. I will be here on and off, and there will be a lady that will keep an eye over the exam. So sometimes I will come and answer questions, but I will not be here all the time. Some things that you should know for the exam. The form is in English and the answers should be in English. Okay, course is in English. Last year, people somehow did not understand that the exam should also be written in English. I recommend bringing some colored pens. Okay, not red, because red is the one I use, and it will be very helpful to draw on outlines and so on with different colors. I recommend bringing a ruler. It will be especially useful if you need to construct a cobweb, but also just for plotting graphs. A calculator. Okay, you might need. Most calculations are simple, but if you do want to estimate some expression with a square root, then a calculator can be useful. Other than that, I think that's it. The structure of the exam, everything I say here I will also post to the forum for the people who are not here. The structure of the exam, there will be one mandatory question that everybody has to do, and then you will have to pick 2 out of 3 questions. Okay, so you can leave out one question. I don't recommend leaving out a topic when you study. Okay, try to study everything. Also, you never know if you'll be able to answer the questions on the topics that you did study for. Okay, that's it for now. How long is the exam? Well, I expect it should take up to 4 hours. I want to think maybe we'll say at the beginning it's 3 hours, but time is not, it won't be so constrained. Yeah, so this year's exam will be shorter, of course, and yeah, it should be doable in 4 hours. Okay. But if you need, you'll probably get time, but not unlimited. Okay. Okay. So what I'm going to do today is first I'm going to solve a question, and I'll use this in order to emphasize a few points that I feel were not understood by everybody, or I want to mention a few things that are more like more formalities. The way that you draw the phase plane. Not everybody understood this. And after that, I might do another short thing, and also I'll answer questions. Okay. Did anyone prepare questions except for Rotem? No? Okay, so you can also ask freely. Okay. This question is about a two-dimensional nonlinear system. And you're given the system. Okay. And you are asked to find you're asked to find the null lines. Sometimes you'll be asked to find the fixed points, but obviously you do that through finding the null lines. You're asked to find the fixed points and classify them. You're asked to draw the phase plane. You're asked to comment on the validity of your classification. This is a point that not everyone understood in the exercises, so I'll go over it. Draw the phase plane. Okay. And finally, you're asked to describe in words what happens in the system. So we can start. Okay, so finding the null lines, we demand that x dot equals 0. Get y equals x to the fourth minus x squared plus 1/4. Then we demand y dot equals 0. We get x equals 0, or y equals 4 minus x squared. Okay. We have one x null line. Okay. This is called the x null line. This is called the y null line. We have two y null lines. Where do they intersect? So first of all, we can substitute this inside this, and we know that our first fixed point is this one. The other fixed point, okay, we can also equate this and this, see the intersection. So we have x to the fourth minus x squared plus 1/4 equals 4 minus x squared. This cancels out. Wait a minute, I had a feeling I didn't want this. What? No, just a minute. Yeah. Okay. This will be 9/16. Okay. Sorry about that. Um, the question went through several modifications. Oh, 5/16. Okay, so the question went over several modifications, and the idea was that here this will be 5/16 minus 1/4 equals 1/16. So x is plus minus. Okay. Okay, so we got two additional fixed points here. And so when we substitute this here, equals 5/16 minus 1/2. This is four, no. And y equals 5/16. Well, they're both the same, because when you take the square of this, it's the same. So other fixed points are minus 1/√1/2, minus 3/16. Okay. I will now draw the phase plane, and this also serves as a verification for the fixed point. So first of all, we have our y-null line at x equals 0. The fact that it's a y-null line means, of course, that it can be crossed only horizontally. Okay. 5/16 minus x squared. So let's say I mark 1, and 5/16 will be just over 1/4. And the intersection of this with the x-axis should be x squared equals 5/16, and x equals √5/4. So √5 is 2 and something, so √5/4 is around 1/2. These are the y-null lines. Now for the x-null line, this might be not immediately plain to everyone, but as you remember, we had our method of looking at what happens when x is small. Okay, so when x is 0, okay, we have 1/4. When x is small, x squared is larger than x to the 4th. So this should behave as an inverted parabola, as a minus x squared. When x is large, then it begins behaving like x to the 4th. So I won't draw this here, but in general, x to the 4th is, you know, it has this kind of shape. So at the large values of x, this will behave like x to the 4th. Another thing you can do is always you can substitute. Just take several values, like x equals 1/4, 1/2, 1, 2. Substitute them, and you get exactly the points where the curve should pass. And I think this is a good method for an exam. If you're stressed and it's hard for you to try and break this down to different regions, you can always substitute. Okay. Where does this cross the x-axis? I can calculate this because I can consider this as a quadratic equation over x squared, right? So I can say that x squared equals 1 plus minus 1 minus 4 times 1 times 1/4 divided by 2. So these cancel out. This is 1 minus 1. So I just get 1 over 2. Yeah. So x itself is plus minus 1 over the square root of 2. And that it should be 0.707. You can check with the calculator. So, okay, this one was I'd like to know where it is in relation to that. Just use a calculator. Okay, so this is 0.56. So the crossing this is square root of 1/2. Okay, another below, because I only got 2 roots. Okay, I did not get 4 solutions when I solved this for x squared. Okay, I did not get 4 solutions. Okay, another thing that I want to stress for the exam is that you should make your plots as big as possible. it will be, first of all, easier for you to use a large plot, and it will be easier for me. So now that I know the more relevant range, yeah, okay, so this will be 1/2. We have this, this, and over there we have, so this is 1/2, 1/4. There. And okay. Now, it's good to label the null lines or color them in different colors, but I only have red here and saving it for something else. So this is a Y null line. This one is a Y null line. This one is an X null line. And remember, the fixed points are only in the intersection of an X null line with a Y null line, right? And this means that this intersection is not a fixed point. This one is not a fixed point. This one is a fixed point, and these are fixed points. Okay. Okay. The next thing I want to do when I have the null lines is try to see where the system goes in each of the regions. So this is what I was saving the red for. What? This one? It's an intersection between a Y null line and a Y null line. So X can change on it. Okay, so on the Y null lines, we have horizontal directions. Also here, right? And here. On the X null lines, we have vertical direction. Now, it remains to see where it goes on each of these lines that I drew. So for this, I go back to these equations and to the original system. And I'm saying, okay, on the X null line, when I am on the X null line, this is this waving curve here. Where does Y go? Okay. So yeah, I'll start from the other one. Okay. I'll take X equals 0. Okay. The Y null line that is X equals 0. and I'm asking what is x dot. Okay, so what is x dot when x equals 0? These will cancel out, right? Y minus 1/4. So if y is larger than 1/4, then x dot should be positive. This is 1/4 here. X dot should be positive, so it goes to the right. If y is smaller than 1/4, then x dot is negative. This is redundant here. We don't really need 2 arrows. Okay, now in a similar way, I'm looking at this null line. That is the inverted parabola. And I'm asking, where does x dot go? Okay, so I'm going to look at large y and small y. Okay, where does x dot go? So if y is larger than all this, okay, so see, y is compared to this expression. So if y is larger than this curve, then x dot is positive. So any place on my inverted parabola, maybe there is a green. No. You know what? I have my own pen as well. Okay, I hope you can see that I'm making the x null line green. So any place on the blue parabola that is above the green parabola should have a positive x dot. So any place above the green should have a positive x dot. Any place below the green should have a negative x dot. Okay, and this is consistent, actually. I see that these are consistent. Oh, thanks. It's just thicker, so it's easier to use. Okay, so this is my strategy for finding the directions. You can even write it explicitly on the form of the exam in your notebook, so it'll be easier. Okay, so say, okay, when y is large, then y is larger than this, x dot is positive, and so on. Yes. Okay, so now I'm looking at the green curve, and I want to see what happens on that. So now I'm looking at the y dot equation. And now I'll need to break it into cases. So it could be that x is negative, right? And y is large. Okay, so say y is large, and so this expression is positive. Okay, x is negative, this is positive. That would be here. Negative x, large y, which means larger than the blue curve. Negative times positive, that's negative. So this goes down. Okay? The complementary case is that x is negative, but y is not large enough. It's not over the parabola. See? here in the green section here, y is smaller than this parabola. So this will be negative. Y is too small to compensate for these, and this expression will be negative 2. And on the whole, y dot should be positive. Okay. And then we will look at the other case. X is positive. X is positive. Y is large enough. Positive times positive is positive. So anywhere above the blue line, this is above the blue line, y will be positive. So see, this is different. It's not symmetric. And when x is positive, but y is not large enough to compensate for these terms, positive times negative equals negative. So negative. Okay. I got all my arrows on the nose lines. I can immediately draw the arrows for the regions. So if this goes right and this goes up, in this region, I'll have this general direction. Here I will have this general direction. The direction that is common to, that is composed by these two, is this one. These two match this direction. Taking these two, I get this. These two, I get this. It's the same here. So I also have the small regions inside. So here and here. Okay. Does everyone understand how to do this? Taking the vertical and horizontal direction and inferring the diagonal directions in between the milk lines. Okay. Now, I want to classify the fixed points. So, I'm going to write the Jacobian. Notice that I first write the general form of the Jacobian, and only then I will substitute any values for fixed points. If the system is given with a parameter a, b, c, then first write the Jacobian in terms of a, b, and c, and so on, and only then substitute. Maybe you'll be asked to substitute a equals 2. Okay, we are considering a equals 2, but write the general and then substitute. Okay, so differentiating this by x gives me minus 4x to the third plus 2x. Differentiating by y gives me 1. Differentiating this by x, I will do this. I'll open the parentheses. So the first term is xy. Derivative is y. Second term is x to the third. So the derivative is 3x squared. Third term, derivative is just minus 5 over 16. Now differentiating by y, this is just x. Okay. Now I'd like to start classifying the fixed points. So first, I will substitute 0 and 1/4. So j at the point 0 and 1/4 equals, this is just 0, right? 0, 1, 0. And here I will have 1/4 minus 5/16. And that is minus 1/16. So the trace equals 0, and the determinant is 1/16. Okay? And if we make our useful delta versus tau plot, we are somewhere on the delta axis where we have centers. Okay? This is Autumn's question that she sent me by email. What does it mean that we have a center? So it means that in the very close vicinity of the fixed point, remember, this is a nonlinear system. So the linearization, if it is true, if it holds, it will hold only at the very close vicinity of the fixed point. At the very close vicinity, there is a fixed point. It's Lyapunov stable, okay, but it is not attracting. This means that, say this is the fixed point. If I deviate by a little from the fixed point, I will not go back to the fixed point. Okay? I will start revolving around it in a closed circle. If I go a little outwards, I will start revolving around it in a closed circle. This is the meaning of centers. It's a kind of neutral stability where closed orbits. Yeah, it's a closed orbit that it's not a limit cycle.
But we have
two complex eigenvalues, right? 2 complex eigenvalues.
So what?
Exactly. So remember, in a spiral, we had complex eigenvalues, and we said the real part can be positive or negative, and it will determine the growth or decay. So here, there is no real part. The real part is 0, and we only have an imaginary part. So we only have the revolution around the fixed point, and we don't have any growth or decay.
And will we need to say something about the direction?
Yeah, but you see it from here. Okay. Well, no. When you say the fixed point,
Because we did showing one of
yeah, with a spiral.
yeah.
So no, you don't need to say, when you classify the fixed point, you don't need to say if it's clockwise or counterclockwise. Only in the drawing you will have this. Okay.
I have another one.
Yeah.
We need to remember the definition of the Lyapunov stable and everything.
Yeah, Lyapunov stable versus attracting. Okay. So this one is Lyapunov stable because if you go a little away from it, you stay in the vicinity. Okay. It's not attracting because you don't go back to it. But you stay in the vicinity, so it's called Lyapunov stable. Okay. So we classified this. This is a center. First, before we go on to the next fixed point, where? This one? You're asking whether it's an exact circle or very near the fixed point, it's a circle, but then it can distort as you go away. Okay. Okay, before I go on, I want you to notice that I can infer the type of these fixed points from my drawing. Okay? Does anyone know already what? Second? Yeah, it's a saddle. If I will zoom in on this, just so we have space, we have the two null lines, and in this region, then the dynamics go out. In this region, they go out, but this section belongs to this region, so they go in and they go in. So it's a saddle. Okay. The same goes for this one. Okay, in, and this goes out, and this goes out. So these two, I already know they are saddles. You might get in the exam a question, what can you say about the fixed points just by looking at your phase plane plot, even before you classify them. And this is very useful because maybe you cannot find the fixed point analytically, or maybe you cannot find its stability analytically, but then sometimes you will be able to say, yeah, it's a saddle. If this were different, you would say, oh, of course, it's a stable fixed point, right? The confusing cases arise when you have something like this, and then you don't know, because it can be, it looks like a spiral, but it can be going outwards, it can be going inwards, it can be a closed, it can be a center. So these cases are confusing, but other cases like this one in the saddle and the unstable regular node should be less confusing. This could also be maybe a regular node, okay? That no, actually, no. I guess it's see. No, I don't see how this can be a regular node actually. I guess it should be a spiral or a center. So in some cases, you won't be able to tell exactly what this is. And other cases, like the saddle and the regular nodes, you will be able to say. What? It can be a limit cycle, yeah. No. Wait, no, I think it cannot be a limit cycle. The reason that I'm saying this is that I cannot see how this type of dynamics can occur around. Oh, there can be a limit cycle. It can be a spiral with the limit cycle around it. Yeah, could be. I guess it could be. Okay. Let's see if we can do something with the other fixed points. Comment on the validity. Oh, I lost my J. There it is. Okay, so J at the fixed point minus square root of 1/2 minus 3/16. So 2, this is minus 2 / square root of 2, and 1 minus 2/2. Right? X squared is is 1/2. So it's 2 over 2. Here I have 1. Over there I have minus 3 over 16 plus 3 over 1/2 minus 5 over 16. And x is minus 1 over square root of 2. These cancel out. I have 0 in the first position. 1. Okay, minus 3 over 16 plus 48 over 16. No, 24 over 16. Minus 5 over 16 equals minus 3 minus, this is 16 over 16 equals 1. 1 minus 1 over 1/2. Okay? So the trace is minus 1 over the square root of 2. The determinant is minus 1. Indeed, this is a saddle. The other case is just with a positive x. So this will cancel anyway. Over here, the x was squared, so it doesn't matter. So 1 minus 1, that is still 0. We have 1 over there. This here, x was also squared here, so we don't care. This is 1 again. And this is 1 over square root of 2. So trace is plus 1 over square root of 2. Determinant is minus 1. And we have a saddle. Okay, now about the validity of classifications. Okay, the point here is that we need to consider two things. We need to consider our classification of the stability and our classification of the type. Okay, so if we are talking about stability, we are saying saddle, stable, unstable node. If we are concerned with the type, so it might be a spiral, star, degenerate node, it might be a regular node, here we also have center. And the idea is that if my linearization gave me a point, a combination of determinant and trace, okay, that is somewhere here, for example. I say it's a regular node. And then I'm asked, okay, do you trust this linearization? I will say yes. Okay. If the second order terms have anything, have have a role that is not negligible, then it doesn't really matter. I don't expect them to lead me here or here. Okay? I'm saying the linearization should be robust to small effects of higher order. I'm saying, yeah, I trust this. This should be first of all, I trust the stability. This should be an unstable node. Second of all, I trust the type. I'm confident it's a regular node. Same goes for the other half of the plane, right? If I got a place that is right here, okay, then I would say I trust the stability. I trust that it's I can be confident that this is an unstable fixed point. However, I'm not sure about the type. Okay, the linearization might not be not be so robust to the second order terms. So it might be that the fixed point is actually a regular node. Maybe it's a spiral. I'm not sure. Okay. Now, if my linearization lands me here, like we had in today's case, then here I'm not sure about the stability. Okay. Higher order terms might mean that I'm actually a spiral with a very, very slow growth or a very, very slow decay. So I'm saying I can't be confident about the stability of this, and I cannot be confident about the type. I identified a center, but there is a slight chance that this is. It might be a center or a spiral. This is what I mean. Okay?
The same thing.
What?
The same thing.
A center and a spiral?
Yes,
So it's not the same thing. It's interesting for me if I will really get to the fixed point, or if this is only Lyapunov stable, and I might end up revolving around a certain sense, around the fixed point in some closed orbit.
So the center of stability is not a type.
The,
Like you would say.
yeah, no, but it's also a type. These types are inside this.
Yeah.
Okay.
So you don't trust either one.
No, you don't trust either one. Okay, for a saddle, I will say, yeah, I got a saddle. Most probably, higher order terms do not play a role, or if they play a role, I don't really care. It will still be a saddle, only a bit different. Here again, I don't care.
If you are not on the line, you're close to the line, so you trust.
Say again? If I'm.
If you are not, you said if you don't trust.
Yeah, no.
If you are on the border, but if you are close.
The way we do it is we consider only the borderline cases as a classification that is not necessarily valid, a linearization that is not necessarily valid, and therefore the classification. What?
If you are exactly on the border.
If I'm exactly on the border, I say that I'm not sure.
You are not sure about the property that the border.
Exactly. Okay. If I'm here, then what I get is a line repeller. Okay. About the line repeller, I want to emphasize a certain point. You might be asked whether the fixed point is Lyapunov stable or not, or attracting or not. So fixed points on a line attractor, each fixed point is only Lyapunov stable. Okay, it's not attracting. If I move a little to the sides, I will remain there. This is the definition of Lyapunov stable. I will not go back, so it's not attracting. When I consider the line itself, the line is an attractor, because if I deviate a little from the line, I go back. Okay? Okay, so if I land on this axis, then again, I will say I got a line repeller or a line attractor, but I'm not confident about the identification, because if the higher order terms take me to the sides, this might actually be a saddle. Okay, so there might be very slow growth on the line, or a very slow attraction to a certain point on the line. That would be kind of the yeah. So if on this line there is very slow growth, then it's a saddle. If there is a very slow decay to one of the points on the line, then it's actually a node. Okay? So this is what we do about the validity. Now describe in words. So
This is the repeller, right?
the line that I drew, oh, this one is a repeller. Yeah.
So you're not sure about the stability.
Either.
Because
I'm not sure about the. Oh, yeah, I'm not sure about the stability or the type, nor the type, I mean, line tractor repeller, because, well, if I am in this half, I can say I'm sure it's unstable, right? But if I'm on this half, I will say I'm not sure about the stability. If it's a saddle, it's considered an unstable point, and if it's a regular node, it's considered stable. Okay, so there is a difference between these two. Okay, now describing in words. For this, I'm going to do something that I did not mention there, or might be part of drawing the phase plane. I'm going to try and draw the trajectories on the phase plane. Okay, and some of you were kind of unconfident with this in the exercises, and
Not that
you don't know for sure, but you make assumptions. So what I want to say now, for the exam at least, is that you're allowed to make assumptions, and you may make some mistakes. Okay, the criterion that the trajectories should meet is obeying these arrows that I drew. Okay, so if you draw a trajectory that crosses like this, that will be wrong. That's a mistake. But anything you do that still complies with the directions on the note line is okay. Okay. So the first trajectory I want to draw is one that comes from here and goes over there. I can be pretty confident about that. The important thing is that it will be horizontal on the line, on the note line. Okay. If you draw, for example, if you draw something like this, this will be wrong because there is no note line here. Okay. Okay, let's take the other part that is away from the fixed point. So there could be a trajectory coming diagonally from here, crossing this null line, going like this. Okay. Another thing that can happen is a trajectory going diagonally. Okay, this is what I did here was okay. This is cannot be right. I cannot change direction from right to left if I don't pass the null line. So I need to erase this. Uh, I was meaning to draw something that goes diagonally. It only becomes vertical on the null line, and then it goes here. And I should have something similar here. Okay, this thing is already in accordance with the pattern of the saddle point that I have here, right? What? Where? Here? Oh, no. Yeah, you're right. Okay, so these things look like what you should get around the saddle. Now, about the marking of the fixed point. On your phase plane, you're supposed to mark a stable fixed point with a filled circle. Okay. If there are cases like this, well, probably I will write in the instructions mark Lyapunov stable points with a filled circle. Okay. Or maybe I'll write it anyway. So here I will mark a fixed circle because it's Lyapunov stable, not because it's attractive. Okay, now what else do I have? I know this is, I classify this as a center. So here I have orbits, and here it's important how you draw these orbits, okay? So it should cross the null lines horizontally or vertically. Okay. Now I'll go closer to the saddle, and I'll try to say what happens there. So I can draw this, even if I did not find the eigenvectors, I can draw this pattern that should occur around the saddle. This stable manifold, it probably comes from infinity over there. Oh, wait a minute, I did a mistake, right? It's an unstable manifold going to infinity. This stable manifold comes from infinity. Well, how can I tell? There are no null lines to be crossed here, so this is how I tell. Okay. This goes over there. This goes over there. A trajectory cannot come from here to here and cannot come from here to here. So it must come from the region between. Must come from the region between these null lines. Okay, so I can do a similar thing here. This is going diagonally into the saddle. This is going diagonally to infinity. Things other than this, I'm not sure of. But it's quite safe to assume that the manifolds of the saddle, of saddles should connect, and a lot of times a manifold will go out of an unstable fixed point or into a stable fixed point. So what I'm going to do here is to connect the manifolds, still, of course, according to the null lines. So the crossing should be horizontal here. Okay, I'm going to connect the manifolds from above. Yeah.
Shouldn't the eigenvectors be perpendicular to both null lines?
I don't think so, but I'm not sure.
Because it has to cross it perpendicularly.
The null line,
Yeah.
but here the I.
I mean, on both, it's either y or x should be perpendicular. So
Let's draw this in a bigger, on a larger scale, and then I'll try to understand what you mean. So these are the null lines and fixed point. And you're saying that one eigenvector should be perpendicular to this null line? No, no. Say the null lines are like this, like here. They have a small angle between them. Then the other eigenvector will be here, and it can't be. They should belong to the different regions that the null lines delimit. Okay.
so then if I have if my starting point is right on the eigenvector,
Right on the eigenvector, yeah.
so how will it go, the trajectory?
Just inside.
And
No, okay, but you should remember that the eigenvector is an eigenvector only in the vicinity of the fixed point. So this thing might, it might even come from a null line that was here. It outside of the fixed point, it might do other things.
so it shouldn't be perpendicular on the fixed point, the trajectory itself.
No. Also, the eigenvectors are not always perpendicular to each other. So
No, I know. This is why I thought that maybe, because we always said that it should be, when it comes,
Yeah.
when a trajectory comes, it should cross it.
the null line,
Yeah.
cross the null line.
And I don't see why it will be any difference on the fixed point.
Oh, I think now I understand what you mean.
If
Okay.
it's like this, then
Okay. You mean that that the directions are the blue one? Yeah. The directions are like this, right? And it should hold right into the fixed point, right? So no, it doesn't have to do with the eigenvectors. So this is, say, this is the eigenvector. This is the instance that this is the instance where this type of trajectory just changes its direction from left to right. Okay? And this is the instance where this type of trajectory changes from down to up. Okay?
Trajectory that's on the eigenvector itself.
The trajectory that's on the eigenvector itself,
Just doesn't cross.
it doesn't change direction. It doesn't change from down to up or from left to right.
No, yeah, but I think the point was that when it should arrive to this
yeah,
point,
when
it
it
should arrive
reaches,
perpendicular.
To what? To the null line.
yeah.
No, no. 'Cause, I see what you mean, but I don't think it goes this way. I think no. Well, I don't know. You can try to check it, but I don't know of such a relation. I imagine that in the very close vicinity, it just, it goes into the null line, but it doesn't cross it because it's going into the fixed point.
Both of them are zero at the crossing.
Yeah. It just goes into the point that's on the null line. But if it would continue, yeah, it would continue, and you would see that it changed direction. But it doesn't continue. So, okay. So these are my trajectories, and now I would like, as the last stage, I would like to say what say in words what happens in the system. Yeah.
Talking about the projector, it makes sense that you connected the saddle, but I wouldn't do it. I mean, how do you know this is what happened?
I don't know exactly. If you don't connect them, it's also okay. Okay. The reason that a lot of times a saddle will connect to a stable or an unstable fixed point is that they originate in a bifurcation. Okay, in a saddle node bifurcation. But
Why they think that?
because as the saddle and the fixed point get closer and closer, you know, eventually they merge. So there is a trajectory that is canceled. You know, there should be a trajectory between them. Say they are formed as a fixed point and they start diverging, then this trajectory, you know, it was created from nowhere.
How do you know? I mean, if I would think about it, how can I know that it doesn't go into a closed orbit? If it goes, I mean,
No, you don't
it's
know.
hard to
You don't
say
know.
something about the connection between the fixed points.
Yes. So this is what I'm saying. This is something that will not be graded. Okay? If you do things that cross the node lines in the correct directions, that's enough. On top of that, you can speculate. You
Why
don't
do
have to
you
speculate.
This is what happens when there's no closed orbit.
I don't know. I have an intuition that everything here is kind of a closed orbit. These are closed orbits, and so eventually there is an orbit that is, it's not really closed, right? But because you would end inside the saddle, here you would end inside the saddle, but as if, you know, things going like this, they should originate from somewhere, right? They cannot originate in the saddle. They cannot originate outside. They should originate from somewhere, and I don't see any place they can originate here. Okay?
Why not from outside?
Because these, well, let me think.
They can originate from the top.
Maybe it can happen like this, but then this unstable manifold, then where will it go? It can spiral maybe into the fixed point. Maybe that could happen, or into some closed orbit around the fixed point. So this is speculation. It's not really. It's not critical that you know how to. You know whether these are connected. Doesn't matter.
So what if we, in the exam, we need to do all these steps,
Mm.
we don't need to connect?
You don't need to connect the. You may connect them. It will not be a mistake. As long as the connections obey the node lines. Okay.
But we don't need to.
You don't need to, right? Okay. So now the description in words. So in words, I would say that there is a fixed point on the y-axis that is Lyapunov stable, and it's I think it is a center. It's surrounded by closed orbits, and basically, in my hypothesis is that the manifolds of the saddle, of the two saddles, enclose a region where everything revolves in closed orbits. Okay? And then I would say, depending on the initial conditions, I can say things, initial conditions from the third quadrant, from the second quadrant, say very large y and very negative x, they might end up in the first quadrant, or they might end up in the third quadrant, depending on initial conditions, and so on. I can describe And then things starting in the fourth quadrant, they might end up in the first quadrant, or they might cross in a wave-like manner, cross the y-axis, and end up in the third quadrant. So I'm interested in where things start and end. Do they end in infinity? Do they end inside a fixed point? Here they don't end inside a fixed point because the saddle's only there. I can say only on the stable manifold things will not end up in the first or fourth quadrant or third quadrant, but they will end up in the saddle. There's also a matter of basins of attraction here. So yeah, okay. Okay, so no, I wanted to say not basins of attraction, but separatrices. Yeah, okay. So anything. Okay, so this would be one basin of attraction, and it's defined by the stable manifolds of the saddle. This is another basin of attraction, and here, this is initial conditions are trapped. That's what I think. Okay, you could try to devise a different behavior of the system. You could try to say things spiral into the fixed point. This is I just want to say that most systems you will get will not be as complicated as this one. Okay, this is a little complicated with the connections, like we said. So we don't really know what happens here. But in most systems, it will be more clear where things go.
Do we have to specify the manifold in the basin attraction? In the Dragon word?
No.
Or
No, only if you're asked specifically. Okay?
How much detail do we need in the word description?
What?
How much detail do we need?
In the verbal description?
Yeah, because we can say we can describe in words any kind of suggestion and any kind of quadrant.
Yeah. We'll try to treat the major cases. Okay. It's interesting. If you have a fixed point, try to say which areas of the plane lead into that fixed point. Okay. Or if it's an unstable fixed point, try to say things starting at this fixed point or near it might go to this area of the plane and that area of the plane. And then you have several fixed points. So major cases. You don't have to say in detail. Say here you don't have to say that this has a wave-like shape. Okay. Just that things pass from here to here. Okay. Yeah.
explain what is blue, what is the red, what is the white?
Okay, so this is a basin of attraction of the third quadrant. So things starting here will go over there. Things starting here will cross and go over there.
I thought the basin of attraction is something fixed.
Well, not only. It's like in geography, with water going to different basins.
But can't you go into the saddle or
Yeah, so in between the basins of attraction, there are these lines. If you start on this line, the separatrix, you go into the saddle. If you start here, you will be trapped here. According to my speculation, that these things are connected. But okay, I wanted to do this system because it has a center, and you asked about a center. So that was nice that the system that I thought of had centers. Also, because this expression might be hard to draw, and I wanted to show you that you can do it by asking what happens when x is small, what happens when x is large, and in any case you can substitute specific values and draw it by hand. Okay. Also this, and so the numbers and the forms of the functions were not very nice, but it was not too bad. Okay, we were able to find fixed points. We were able to tell their stabilities, even without analyzing the stability. We knew that they are saddles, for example. And you might get a question like that. Okay, so here, please say what can you say about the type of the fixed point? And it will be stated, you do not need to locate the fixed point, or you do not need to analyze its stability analytically. Just say according to the directions that you drew. And then you can say, yes, I see this is a saddle, I see this unstable fixed point, I see this is a stable fixed point, or I cannot tell. This might be a spiral, an unstable or stable spiral, I cannot tell. Okay, so that's it for now. Do you want to take a break? Anyone? Say yes if you want to take a break. Yeah? Okay. So we'll take a 10-minute break. That's okay? I can stay until 12 at least.
ואגב, אני באמת לא מבין מה יש לי להסביר. באמת.
מה השיטה שלך
עשיתי בראש.
כאילו בראש, לא.
חיפשתי משהו שאני גוזר אותו לפי X אני מקבל את זה, לפי Y אני מקבל את זה.
לא יכול להיות.
כן, נכון.
לא, אבל סוד, כאילו,
לא, נכון,
באמת
זה
שנה
נכון,
א'
כי-
סמסטר א', של תואר ראשון.
אני חושב אחרת. אני חושב שלאורך כל תואר ראשון היית צריך להראות מה...
הראיתי בשנה א', שנה א' כבר לא הראיתי, גם בג'.
אוקיי.
אז בטח שגם פה.
לא היה להם כוח לבדוק, לא יודע.
לא, כאילו...
פשוט, להראות איך הגענו לדרך.
הכי טוב אינטגרל זה ב-X. לא מסכים, אבל בסדר. מה אתה אומר על זה לזה?
אני רוצה לעשות סימולציה.
אני תמיד רגיל להסתכל...
תגיד שמה הביטוי?
לא חשוב, אז כל מקרה, יש לך עכשיו וקטור עצמי אחד עם יותר גדול מהשני, איך אתה מתאר מהשני? משווה סימן. מחר בצירים הראשיים, מחר אחד עם...
אוקיי, בוא נסתיר. מי שאנחנו בנקודה אחת וחצי.
עם המערכים עצמיים.
פשוט יהיה לנו x שווה 5x, y שווה 2y.
זה 5 יש לך. זה 5.
בנקודה הזאת, כן, אז יש לי...
פה אתה E בחזקה 5.5.
זה בעצם
פה אתה E בחזקה 1.
למה היא בחזקה 1?
אתה מתחיל את הנקודה חצי.
זה כאילו 2.5 וזה...
כן.
x זה שווה וזה y זה שווה.
אתה הולך לתחזק עכשיו ב-X.
כן. אוקיי, בוא נסתיר את הנקודה 2.
זה 10.
10 וזה 4. זה חלקי זה 5 וחלקי זה 2 וחצי.
זהו, 2 היה לך 2 וחצי.
נכון, כן.
2 וחצי.
זה לא טוב מה שעשיתי. הרעיון לקחת את הנקודה בין 2 וחצי.
לא, אבל אתה רוצה שנקודה שאתה עובר פה, אתה עובר פה.
כן, אתה רוצה לבנות מסלול.
כן, אתה לא יכול לבחור כמו נקודה שאתה שם.
אתה פשוט באינטגרציה, אתה יודע, אני יכול...
אם אתה יוצא מפה, אז אני לא יודע אם אני בכלל עובר פה.
נכון.
אני לא יודע אם משמעות יש לזה.
לא, אם אתה יוצא מפה, אתה עובר פה.
למה? אתה יודע איך לא חצי חצי ולא בחצי חצי ועוד איכשהו.
אם אתה פה ב-0,0 אתה נשאר ב-0,0. פה איפשהו יש נקודה שלה.
אוקיי.
כן, אז כאילו זה אי אפשר באמת.
אוקיי, סבבה, נכון. לבחור עוד אחת שאתה...
זה לא באמת להביא סימולציה מלאה. שיוצא ביום.
עשינו את זה הרי לתחילת הקורס, לא מזמין, אתה הולך יותר חזק לכיוון הזה.
נכון. עכשיו נגיד שזה ככה, יש לך 5 של x חמישית, y ועוד שני y, אז אנחנו אומרים
שלך היא יותר חזקה עד X. מפה אני קודם כל דרך עד X ואז אני דרך עד Y.
ואיך חוסמים את זה?
זה
זה אמור להיות כאילו רק חץ מתחלף.
כן, כאילו. טוב, אם אני אגיד בנקודות כאלה נגיד, אני יודע שהוקטור שלי יהיה כזה, אני יודע ש X גדל יותר מהר. בנקודות ש-X מאוד קטן, Y מאוד גדול, אז יכול להיות ששני Y יהיה יותר גדול מ-5X.
ואתה חושב תמיד נכון? תמיד גם במקרה של הערכים עצמיים, כאילו, ואני יכול להסתכל על המקרה של השליליים ולראות מה המסלול לכיוון של החץ.
כן, אני חושב שזה נכון.
זה תמיד...
אני חושב שזה יהיה נכון.
טוב.
אני חושב שזה תלוי באמת ביחס בין X ו-Y. כי אתה יכול לצייר קו שמצד אחד שלו 5X תמיד יהיה יותר גדול מ2Y, מצד שני שלו 2Y יהיה יותר גדול מ5X.
הייתי מצייר את האלכסון. אני מצייר את הדעת שהיא של 2 אולי, או Y שווה 5, אז דברים אחרות שמשנה 1.
אתה נכון לזה?
כן, זה המקרה שאו שפה תחליף את זה ב2, או שזה תחליף ב5.
כן.
ואז, אוקיי, אז נגיד שזה 5, אז מה קורה אם הוא הופך ל2, או מה קורה אם הוא הופך ל6, ואז אולי לחשוב אחרת.
כן. מה שאני רוצה להגיד זה אוקיי, נגיד שזה מינוס 2X וזה מינוס Y. נשמור על יחסים. יש לי את הקו Y שווה 2X. בכל הנקודות פה, Y הוא יותר גדול מ2X. אז Y ידח יותר מהר. כאילו, גם אותו דבר לפה. כל הנקודות האלה, Y יגדל יותר מהר מ-X. בכל הנקודות האלה, Y יגדל יותר לאט מ-X. וזה בסוף נצטרך לשאול.
עכשיו, לימיט סייקל זה... אני לא צריך לעזור, אם אני יודע תקופה אני כבר לא אשאר בלימיט סייקל, נכון?
או שאתה תחזור ללימיט סייקל. תלוי אם הוא יציב אולי.
אוקיי. עכשיו הראינו ש... אפשר להגיד להראות שאין לימיט סייקל.
כן.
אני לא רוצה אין סכום סוגר. אז אני אומר שאין, אבל אוקיי. אם לא מצאת סכום סוגר, שאין בכלל? לא. זה רק דרך להראות שאין. זה לא דרך להראות שיש. איך אני אומר שיש?
הדרך היחידה שלך היא באמת להראות שזה משפט קונקולר בנדיקסון
מה, אם יש לי איזשהו שטח
שאתה יודע שדברים חייבים להיות תלויים בתוכו והוא לא מכיל פיקס פוינט.
גם פה אני יכול לפרוש אינדקס. אם אני בוחר פה שטח כזה של דיסקה וכזה זה פיקס פוינט, כן?
כן, זה דיסקה.
כן? שיטה אחת דיסקה, יש איזה סיבה של פיקס פוינט. הרי פה אין לי מצאתי, נכון?
אתה צודק. לא, קונקולר בנדיקסון הוא ל-closed orbit function.
מה זה?
קונקולר בנדיקסון הוא ל-closed orbit. זה יכול להיות גם ל-closed orbit.
אוקיי, אז תבחר פה. תבחר דיסקה מסביב בצד על זה.
טוב, מסביב בצד אתה יודע שאין לך דיסקה שחולק מסלולים.
לא הבנתי, אנחנו אומרים תבחר דיסקה.
שלא מכילה פיקס פוינט?
נכון, אז הנה, בחרתי דיסקה שם של הפיקס פוינט ויהיה בלימיט סייקל.
לא, אבל בכלל קיימת התנאי שעל כל הגבולות שלה דברים, המסלולים נכנסים אליה. אז פה מסלולים יצאו ממנה.
כן, אמרנו את זה?
כן. אז זה מה שאני אומר, שזאת זאת הדרך היחידה שלך באמת להראות שיש closed orbit, אבל היא לא... אתה יודע,
אם הייתי בוחר את זה פה הייתי מקבל שפשוט... לא הייתי יודע אם זה לימיט.
כן, כי אתה לא יודע...
לא יודע אם זה לימיט סייקל, אני רוצה שתקלו דורבי.
נכון, אתה לא יודע.
פה בדיסקה נראה לי הכל נכנע, נכון?
השאלה אם אתה יכול לבנות דיסקה שבה באמת הכל נכנס אליה. כאילו, אתה יודע, אם הייתי לוקח...
לא, לא הכל, יש את הכיוון הזה.
אם הייתי... נכון, אז תגיד.
נראה לי שאפשר להתקרב את הכל בשביל להעיר.
רק אם אני נמצא למניפול.
לא יהיה. לא יהיה בכלל. בגלל זה אני אומרת שכאילו אולי אפשר לחכות, לשאול מה האופציה.
כן.
לראות לך מי
לא רואה. העניין המשפט הזה שהוא יכול לעשות רק עם מקרים מסוימים, אבל לא יהיה...
רק אם יש לי פוקס אני יכול להפוך את הקורדינטות בטעות לפולריות.
כן, אז יש את זה זה חלק מהעניין פה שאנחנו... במערכות הלא ליניאריות האלה הרבה פעמים אין לך הרבה מה לומר.
אני יכול להגיד שאין.
אתה יכול להגיד שאין, אם יש לך, אם הגרדיאנט אצלנו, לאפינוס פונקשן.
אבל אם לא מצאת, אם אני ניסיתי למצוא לא צריכים למצוא לאפינוס פונקשן.
אז אתה לא יודע.
זה אומר שאין, אולי יש ולא צריכים למצוא אותם.
נכון.
גם לא... אוקיי, ומה היה?
זה הכל כלים שהם כאילו דברים שבעזרתם אתה מנסה לקבל רמזים על המערכת, אבל זה לא מאוד ריגורוזי, כן? אתה לא יכול הרבה פעמים לנתח את המערכת עד הסוף.
מה היחס בין גרדיאנט סיסטם לדיאקונות?
אני לא בטוח. כשזה גרדיאנט סיסטם אתה לא תמיד יכול לבנות דיאקונות פונקשן.
אבל אמרנו שזה...
הן שיטות משלימות.
אמרתי שאם הצלחתי למצוא פוטנציאל, אז אמרנו ש...
למצוא פוטנציאל?
כן, אז אין לי סייקל, נכון? גם
אין לי סייקל. אין כל זורבי.
כן, לא, אין לי סייקל.
אין כל זורבי.
לימיט סייקל יכול להיות?
לימיט סייקל הוא מצא פרטי של פוטנציאל.
אז רגע, אז אני קודם מסתכל פוטנציאל, אני רואה אם לא הצלחתי למצוא פוטנציאל, זה אומר שאין בכלל שום כל זורבי. יכול להיות שמצאתי...
אם מצאת פונקציה פוטנציאל, אז אין כל זורבי.
אוקיי, יכול להיות שלא מצאתי פונקציה פוטנציאל, מצאתי דיאקונות?
כן, ואז זאת אומרת אין כל זורבי.
לא, אוקיי. איך אני אמרתי? מצאתי פוטנציאל, זה אומר שיש לו...
אין, שלא יכולים להיות.
זה אומר שגם בדוק אין לימיט
זאת
סייקל.
מערכת משמרת, היא לא...
אז זה גם אומר שאין בכלל לימיט סייקל.
נכון.
אז זה כאילו תנאי חד מעט.
כן.
עדיף לבדוק את זה לפני שאני מנסה לעשות דיאקונות.
גם על יפנו ויקטור זורבי. גם על יפנו ויקטור זורבי.
לא, אבל שיהיה לימיט סייקל. גם? אז אני לא מבין מה היה.
כל זורבי לימיט
לא,
סייקל.
בין יפנו ו... יש
מערכות שהן לא מערכות גרדיאנט, היית יכול לחשוב שיש להן, שיתכנו בהן closed orbit, אבל אתה יכול למצוא להן דיאקונות פונקשן, ואז כן לשקול את closed orbit. הן משלימות, הדיאקונות פונקשן זה מין ניחוש שמשתמשים בשורה מאוד פשוטה של דיאקונות.
דיאקונות שקיימת בדינמיקה של הגרדיאנט בדרך כלל? כן, אבל ככה אני מוצא אותה.
אני צריך לחשוב על זה, אני חושב שכן.
ככה אני מוצא, זה אחד מהתנאים שאני מוצא אותה, לא?
לא.
לא, אני רק צריך שפי דרך יהיה קטן מאפס, זה יהיה גדול מאפס. אני לא חושב שכן דינמיקה גרדיאנט ככה.
נכון,
לא, פה אני שמתי לב תמיד שאנחנו מסתכלים.
start this lesson with Rotem's question. Rotem asked, what was the in the N6 outbreak model? What was the meaning of the S versus K plot? Right? We had a plot where we plotted on the S versus K plane. Yeah. I'm trying to open the solution. Okay. Okay. So I'd like to review a little how we got this, and this type of plot is derived from the bifurcation diagram. Okay, and we had, okay, this was S, and this was X, and we had fixed points in the system, and the location, the value of the fixed point, okay, it was dependent on S and on K. So, for example, at large K, no, let's start with a small K. So at a small K, you would have, say, this bifurcation diagram with two saddle node bifurcations. And this means that for different regions of S, you have different behaviors of the system. Okay? It means that when you are given a system with a parameter K that is small and S that is okay, an S that is large, then you have expression of the gene. The only fixed point that can exist is at high X. So this is expression. When you have a system with a small S, then you have a silenced gene. And when you have a system with a medium S, then you have three fixed points existing, and two of them are stable. So this is bistable. And then when K is large, so let's say that K grows on these plots from one to the other. As K grows, the shape of this bifurcation curve might change until eventually it will be smooth with no stability changes and no overlap. Okay, no existence of two or three fixed points for the same value of x. So here, the bistable region is this, and here there is no bistable region. So you could plot for a whole plane of S versus K, you could plot the extent of the regions, of the silenced, bistable, and expression regions. So this will be plot 1 and plot 2 and plot 3. So this is X versus S, or what I'm interested in the different regions along the S-axis. So plot 1 will be this one. As you go and increase S, you have a small region of silence, larger a moderate region of bistability, and then expression. And plot number 2 would be this one. Okay, more a silenced region, a small bistable region, and then expression. And plot number 3 will be this one. So you could think of making an infinite number of such curves and putting them one next to the other and getting the full extent of the bistable region on the S versus K plane.
And just explain how we got this line when we calculated the expression for S as a function of X and K as a function of X as a bifurcation point. And I don't understand the meaning of this line. What is the relation between this line and what you just said about?
Yeah. Okay. So the lines that separate the different regions on these plots are the S at the value of the the value of S at the bifurcation. Okay, so the borders between regions are specified by the bifurcation points. Okay, so here this is a bifurcation point and this is a bifurcation point. And the way we found them, okay, the way we found this relation is we solved for f. Okay, let's go back. We had some x dot equals f of x minus g of x. We started from this, and it was g of, I don't remember where s and k went in. Do you have the solution? Okay. Now, we had, yeah, we had two conditions. So, yeah, this is what I'm getting at. We said that, first of all, the condition for a fixed point is x dot equals 0, right? So we plotted g of x, and we had this function f that depends on x and on s and on k. And we said that when they meet here and here, then x dot equals 0, and this means there is a fixed point. So f minus g yeah. So the general form, the phase portrait, will look like this. This is just f and g, but the phase portrait has x dot, which is the difference. So the difference between them looks like this, and we have here an unstable fixed point and here a stable or half stable. We don't know. We don't care because we're concerned with the positive x. So this is the phase portrait of this. And then, so this is the condition for the fixed point, f equals g, right? But we'd like to know where the fixed point appears, where it first appears. So here there is another fixed point. Okay, so the appearance of the fixed point, these markings, they don't mean anything. The only markings that are mark fixed points are here. The fixed point appears when, let's draw this in blue, say that G has either G or X or F are different, and now they only have one intersection over there, and it's instead of these two. So instead of these two, there is one. If the blue curve will be even higher, there will be none. So here, there is the condition G equals F, but there is also another condition that they are tangent. Okay? So, and this condition is G prime, where prime is d over dx. Yeah, okay. F df over dx equals dg over dx, which is like saying dx dot to dx equals 0. So our two conditions were the condition for the fixed point and the tangency, which is a condition for bifurcation. I think it is. let's think of the transcritical or the pitchfork. Okay, so a minute. Okay. So remember the pitchfork bifurcation. The pitchfork bifurcation occurred when we were passing between this case and this case. So this is this is unstable, and this is here stable, unstable, unstable. Yeah, no, it holds also for the pitchfork. You see that the slope here is 0. So here we have x dot equals 0, but also dx dot to dx equals 0.
So what was the question?
The question was whether the conditions for the bifurcation, the two conditions that allow you to find bifurcations, x dot equals 0 and x dot has a slope of 0, whether it holds only for the saddle nodes or also for the pitchfork and transcritical bifurcation. Okay, so it does hold. Okay, this was
What do we know about the stability of I mean, in this case, it's not stable, but in general, we can say something about
say again?
Generally about the stability of these kinds of fixed points where the slope is 0.
So
This is the more complicated one.
so they are half stable. So they might be half stable, or they might be like here. So this is not. Oh yeah, this is good. Yeah. Okay, this is unstable, but it has a slope 0. So remember when we found the stability analytically, we said that if the slope is 0, then further analysis is needed. It could be half stable or stable or unstable. Okay, so this was this is x to the third plus rx. So here r is negative, here r is 0, and if r is positive, then we have this case, okay? And here the slope is not 0. So we go from a positive slope to a 0 slope to a negative slope, and at the bifurcation we have a 0 slope. Okay. Trying to remember is. Okay. And it's true also for the transcritical bifurcation. No. So for the transcritical bifurcation, I start with positive R, and I go to R equals 0, where the slope of x dot is indeed 0. And I go to negative R. And this is the bifurcation point where these two fixed points collide, and from now on they diverge, but with exchanged stabilities. So the conditions are just generally conditions for bifurcations. So what we did is we found these conditions, and we solved. We found a relation between S and K that meets these two conditions, and that relation is the curve that we draw here. Of x and k as a function of x. Okay, that's a parametric curve. So, yeah. So when you have s as a function of x and k as a function of x, it's like it's possible that from here you will be able to extract x as a function of k, and then combine them and find s as a function of k. Okay, that would be a good case, but not always you can solve for x. So a trick that you do in order to get around this is that you just substitute values of x, and you get the k, and you get the s. So, for example, this would be x equals 1, x equals 2. Each value of x would give you a certain coordinate here, and then you can plot the curve.
So, and on the line, it's the bifurcation.
Yeah.
Possible combination of x and k and x.
Yeah, that give a bifurcation. Yeah.
And the cusp point?
Okay, so the cusp point. This is something I'm not sure how to explain without trying to draw a 3D drawing. You need to try and visualize it. So, okay, we had our bifurcation curve, right? And when we look from above, we will call this region silence, and this region bistable, and this region expression when we look from the above. So you should imagine, in order to visualize the cusp point, you should imagine this as a 3D surface that you're looking at from above. Okay? And the bistable region is the area where the surface folds on itself. Okay? Can you visualize the folding? Yeah? Okay. So the thing is that the folding might stop at some point. There might be a place where the folding begins. This area, this extent, it becomes narrower and narrower until, okay, so I can draw, the slices of the surface, okay, slices coming from different from different points on the surface. Okay. So in this slice, there is a fold. In this slice, the fold is smaller. Here, it's not overlapping itself. And here, it's just a slope going uphill. So the cusp point is the place where the surface is starting to fold on itself. Okay, I think if you want, I can show you later. I have some plots of this. So because this is not important for the test, I think it's not so important to visualize a cusp point, and I don't want to go on. But if you have a 3D plot in MATLAB and you play with it and you turn it around, then I think it's easier to see. Okay, any other questions?
General question.
Yeah. Okay, think about it. Okay. I would like to, as the last question that I will actually do as an example, I would like to do a cobweb. I think we did it once or twice, and I'm not sure it's clear. So we'll take a system x of n plus 1 equals square root of xn. You know what? Let's do this. Okay? Where r can be positive or negative. Okay? So we'd like to find fixed points of this. Okay? So we could go by two ways. We could try to find this analytically, and we could try to find this graphically. Doesn't matter which you pick first. Sometimes the graphical method will be easier and will help you have a handle on the analytical solution. But okay, analytical. How do we do this? We know we say that xn plus 1 equals xn. So if we arrive at a fixed point, it means that there is no longer any change, right? So we say that xn equals square root of xn minus r, and I'll take the square of these two. I'll pass things around from side to side, and I arrive at a quadratic equation on x. And then xn, or I can already write x star equals 1 plus minus 1 minus 4r over 2. So now I can say, okay, so if r is too large, then this will be imaginary, and x star will be complex, and there will be no fixed points. And then if r is 1/4, I will have one fixed point. If R is 2/4, if R is smaller than 1/4, I will have two fixed points. So you already see that there might be a bifurcation here. If R is too large, there are no fixed points. R equals 1/4, there is one fixed point. Smaller R, there are two fixed points. Okay? So 0, 1, or 2 fixed points, depending on the value of R. And okay, so graphically, what we do is we draw this map that maps xn into xn plus 1. We always draw the diagonal. Sometimes x might be also negative. Here, if R is negative, then it's possible that x will be negative too, because then the root will still have a positive argument. Okay, so this is our diagonal, xn plus 1 equals x of n. And then we have this square root function. So a square root function, say R equals 0, it will look like this, right?
But starts from R.
What?
Where it equals 0 when xn equals R, not 0.
When R equals...
When xn equals R, then
No.
your function equals 0, right?
Yeah, always.
For R equals 0?
Yeah. Okay, this is for R equals 0, or maybe I'll try to make it bigger so the interesting area will be larger. There. And this should be 1, right? And this should be monotonically increasing. R equals 0.
Why should this be 1?
Because the square root of 1 is 1. If R does not equal 0, then this curve will be shifted here, or here. It will be shifted horizontally on the x-axis. Okay? Here I already see that I have two fixed points, right? And I don't know their stability yet. I have an analytical tool of checking their stability. If you remember, we said that f dot at x star, we are looking at the absolute value, not f dot, f prime at x star. So f prime is this is x f prime, and then I can substitute my x star each one at a time, and then I'll get some expression, and then I will say if this is larger than 1, if the absolute value is larger than 1, then this is unstable. If
Always loud.
No, after 1.
always larger than 1,
Yeah, you have a square root, it's always positive.
no, but you're dividing by it.
Bigger than 1.
Yeah, if the absolute value of this whole expression larger than 1, unstable. If it's equal than 1, then we need to go to higher order terms. And if it's equal to 0, this is a super stable fixed point. These conditions, remember, they are different from the conditions in the dynamical systems. These are for maps. In the dynamical systems, it was, positive, negative. If it equals 0, you go to higher order terms to see if it's half stable or not. But in the maps, in the one-dimensional maps, the condition is on the absolute value, and you're looking whether it's larger or smaller than 0, okay? Than 1. Than 1. Anything smaller than 1, that's stable fixed point. So I already, okay. Now here, this is a very convenient case because it's easy for me to know the slope of this thing at the fixed point. I have the diagonal to compare, right? The diagonal has a slope of 1. So here, my curve is steeper than 1. Then I would expect this fixed point to be unstable. And here it is less steep than 1, and I would expect it to be stable, right? So finally, I'd like to construct a cobweb for some initial condition. So let's say I start from here. In the exam notebook, you have a grid. It's easier to do this. And if you bring a ruler, then it's even easier. First thing I do from my x0, I go to the curve. I map my x0 to xn plus 1. Okay? This is why it's called a map. You map this to this. Next thing I do is I go to the diagonal, like this. Then I go again to the curve, to the diagonal, to the curve, and so on and so on. And here I am going step by step into the fixed point. If I do it from another x0, then I go to the curve, to the diagonal, and so on and so on. Okay, so I did see that this is a stable fixed point. It attracted all my initial conditions. And this, I just wanted to give a reminder and show you the principle of constructing a cobweb. This is stable, but it is possible, I could have a case where things would diverge to infinity with an unstable fixed point.
What is a cobweb? A cloth?
Yeah, a cobweb is a spider's web. So
This is for r equals 0, right?
this is for r equals 0. So you could imagine that.
Because there are situations where r is either too big or, I think,
Yeah.
that it will go into.
Okay.
It will converge.
Let's do this. Xn plus 1. So I draw the diagonal and say that r is very positive. Negative. See, negative. I want. No, I want. Okay, let's say that r is positive. Okay, and there is no.
Okay, yeah.
There is no fixed point, actually.
But if r is very positive?
R. Let's say I substitute x equals 1, and I want to get 1 minus 1. I want it to be 0. Okay, I want to cross a 0 at 1. Okay, so r is positive. R is positive. And here, let's say I pick an initial condition. First of all, I'm limited, right? Can't have all initial conditions because in the square root I'll have a negative value. Um, so I think, yeah. Here I no longer have where to go, right? I'm starting to get imaginary, complex numbers. But here it will be different. I expect. Let's see. No, yeah, I will always go and start having complex values. But I have no fixed point. I have.
So on
If this were a
maybe not here, but if it was like a actually I'm not sure what I would
It can go around the complex.
because I remember situations where it kind of you just get into chaos because
yeah,
you can't ever it doesn't
reach
converge
the
anywhere.
yes. Yeah, there are cases.
But do we need like so we need to know how to draw the different cobwebs for the different
Cases of
values?
R, for example.
Yeah. Or is that
It's the same. So here you would draw and you would tell me this goes into invalid ranges of x,
okay.
and this could shift over there, right? So and then this fixed point would be here, and
So we need to draw it for different initial values. Like we
for different x0.
yeah, like I'm
Or
trying to understand like what exactly because we didn't do a lot of
yeah.
how do we didn't have exercises.
Yeah. So this is you should know how to draw the cobweb. So I showed you for r equals 0, but you could do it for r equals -1. For r larger than 0, then this is not so trivial.
Yeah.
We saw that. Yeah. Well, I can say that you won't have you won't have very difficult cases with this. Okay. Because I know we haven't done many cases, but you'll have to. You should know how to do this for the more simple cases. Okay. I won't ask you to do a cobweb that has chaos. You won't need to start doing the chaotic mapping or period doubling, which is very much dependent. You won't have to draw the cobweb with the period doubling. This is very much dependent on your accuracy. So you might not get exactly period doubling. But the cases where it either converges to a fixed point or diverges from a fixed point, that is something that you should know how to do.
In the right
No,
in the right case, if we said that we get invalid leaves and
yeah.
complex, I mean I see that we have nowhere to go mostly, but more
You cannot go below here because then xn minus r is negative.
but you said that we get invalid and there's complex and
Yeah.
what could what
The numbers are complex. The, it's out of range. X.
What will happen when we get there?
So if I would run a simulation, I would put a boundary, a lower boundary. If x is smaller than that, then set it to the lower boundary. But
The trajectory stops there.
yeah. But say for a physical system, you should not get this case. Okay. For a physical system, you should say if my x is, say it's only positive, it's like a population, then r can never be negative. Can never be positive. Okay, because then I will start getting complex things. So when I build a model of a physical system, I need to put it to make sure that it won't give me complex values for real quantities.
I have a question, general question.
Wait a minute, is that the question from before?
Yeah.
Okay.
I mean, you said that we'll have something
No, but because there aren't many things to remember. So you need to remember the normal forms of bifurcation and the delta versus tau plot
Delta versus what?
versus tau. Determinant versus trace plot. You need to know, given a determinant and trace, you need to know what is the type of
Yeah, of course.
I don't think there's much else.
Yes, that's
there
what
is.
and all these conditions.
Oh yeah, conditions for stability.
So if you have a system and you know to analyze it and there is nothing I need to remember. I mean, besides to analyze stabilities and there is no voltage. I don't know. I have need to, but beside analyzing dynamics of systems,
Yeah.
is there anything I need to remember biologically or?
No. No, you don't need to know anything technical, any biologic facts or physical facts. Okay, so
And you also didn't mention stochastic processes in the Topsford exam.
Yes, because they're not there.
There's
They're not.
Explain the curve half of an
They're not on the sheet. Yeah, it's because you didn't have you didn't submit exercises on that topic.
But 6, 7 are stochastic processes.
Yeah.
So we did submit
What?
after the test.
Okay. You can write me by email or set a meeting. Okay.
כאילו ב-3D, כאילו אני לא זוכרת אם לא ממש הגענו לזה, סיימו את זה, אבל
שם? הפונקציה הזאת היא לא תוצאות הפרויקט.
But it has
זה
two games
מתאים כפליים, אם
that
לא, אז
scored that take a goal like
המבחן זה
240
התרגילים.
80-20.
includes the
לא,
overtime.
לא בדיוק, אבל
That was
מה
the
שהיה אמור להיות
finding.
פרויקט, באותו יחס.
Besides
אמור
that,
להיות פרויקט.
Ruth,
לא, זה יהיה בשביל.
יאללה ביי.
נראה לי רק הרבה עדים
מה?
כאילו,
מה?
כדי שאנשים יעשו את זה, אולי כדאי קצת להגדיל את ה...
למה?
לא, כן, בטח שלא נרצה לעשות את זה, אני לא רוצה
מי?
לסבוק.
אוקיי. חסר?
לא, אבל תיתן את ה10% האלה למבחן או לתרגילים, מה שיהיה יותר גבוה. כן, זה השאלה. עדיף.
פשוט תיתן את ה10%.
כן, האמת שזה פתרון יותר טוב.
מה זה הרעיון?
נוכחות.
גם אפשר, זה די...
המבחן הוא לא 30%? התרגילים הוא לא 30?
לא.
אז מה זה 10?
היה דף בתחילת הסמסטר שפורסם באתר.
כן, הוא אמר פרויקט 10%. לא שמענו על אפשר לשאול משהו פיזי?
כן.
כאילו, האמת יש לי כמה שאלות פיזיות, אבל אני רוצה לפתור לך אותה בישיבה. מגיע אנשים ממש שמשגע אותי. נגיד הגענו למצב שזה גם בספר. ואז אני לא מבינה למה שאני הולכת 1, 2, 3, ואז אני חוזרת ל4. למה אני לא ממשיכה ל4 לכאן? כי איך אני יודעת? אנחנו עכשיו רוצים לזכור כמה סיבובים היו. אז אני הולכת מ1 ל2, מ2 ל3, ואז מ3 ל4, כאילו חזרתי אחורה. איך אני יודעת? אחרי שתיארתי את הוקטורים. זה משגע אותי, וגעתי מפגרת,
את לא יודעת אם זה באמת איזשהו סיבוב.
כן, נכון, אני יודעת. אז עדיין, גם בא, כאילו,
נכון, באמת.
כאילו, אני לא מבינה למה בכלל באינטואיציה, כאילו, אני מבינה שאם אתה תגיד לי זה הסיבוב, אז סבבה, אני אקח נקודה פה, אני אהיה יותר, אני אקח נקודה 3.5 ויהיה שלך. אבל מלכתחילה בכלל לא הייתי עושה את זה כול ימין. לא, רק שיטה חשבת, כאילו, האינטואיציה.
הוא יותר קרוב. זה הגיוני להניח שתעשו את הנקודות הסתם. אם הנקודה שלך על המקום שלך לא מאוד מורחקות, אז זה הגיוני משהו כזה, כן. טיפות שלא עוברים מניפולד או משהו כזה.
אז זה מה שכאילו, שאתה נגיד מתאר את זה, אז מה עובר בראש?
אתה מניח שהנגזרות באמת...
היום זה לא יכול מספיק קטנות, שתמיד יעמדו לך,
כן, שבאמצע לא קוראים דברים משוגעים.
כן, אני כדאי שזה על ככה.
כן, כי זה כאילו נגיד, בחרתי לי מסביב.
זה יכול להיות או ככה.
זאת אומרת, 1, 2, 3, 4. 1, 2, 3, 4. זאת אומרת ש4 כזה, 2 כזה.
זה מה שמשנה.
1
כן, זה משנה לך. זה יהיה...
אז הנה, נגיד בין 2 ל-3, אבל אם נגיד זה בין 2 ל-3, אתה לא יודע בעצם.
לא,
לא יודע אם זה.
נכון, אז אני חושב.
עוד
בנקודה שלי כזה. כן.
זה ממש יותר מוזרה, במיוחד שתיק חשבת.
לא, אני אומרת,
לא, אבל מי מנסה לקחת? לא הבנתי
נכון, אני אפשר.
הבנתי, נגיד יש לי, זה מה שיוצא לי,
אז פה כאילו...
אבל זה כבר...
אני אומר שהגיוני להניח שזה כזה דבר, כן?
אבל זה כבר בבסיס של הערכים העצמיים.
ככה?
כן.
אתה אומר לך
זה הכרח.
בגלל שזה 2-2?
בגלל שזה על האלכסון. אז אומר כל אחד 0, 2, 0, 1, 2, 2.
אז בוא
נתחיל עברתי מפה לפה.
2, 2, נכון שזה 2
מי שאני מתכוון
מינוס, אבל לך סתם משהו כאילו לא מסגן.
אין כאילו גם מה ההגדרה של קטן, זה
6 זה J.
קטן זה...
אוקיי, עכשיו 2 מינוס למדה, 0, 6, 2 מינוס למדה. זה A מינוס
אנחנו מנסים להגיד דברים איכותיים על המערכת. בלי לעשות עבודה כמותית.
שווה 2 מינוס למדה בריבוע. זהו. כן, זה יוצא 0. מינוס 0. למדה שווה 2.
זה גם חלק מהעניין.
אוקיי? עכשיו, זה הפולינום האופייני שלי. עכשיו אני רוצה לדעת על הוקטור.
בין מתאר ראשון וכאילו
כמה וקטורים יש?
הרבה פעמים מצפים
ואני חוזרת לפולינום
מהמדע
שלי, נכון?
להיות מאוד מדויק.
מציבה את הלמדה הזה.
לפעמים להבין שהרבה פעמים משתמשים בקירובים והזנחות ושיטות שהן יחסית איכותיות בשביל להגיד
כתיבה
כמה
זה
שאנחנו
יוצא לי
יכולים על
0,
מערכות
6.
שקשה מאוד לנתח אותן. מערכות לא לינאריות למשל, הן מאוד קשות לניתוח
עכשיו מה?
אנליטי בדרך כלל.
אז יש לך רק וקטור אחד, נכון?
ואז
יש לך איבר מוביל אחד?
כלים שכן אפשר
שש?
לעשות
אבל זה
סירובים,
כאילו עכשיו עבר מוביל
שנייה.
למקום?
שנייה, עכשיו
זה בערך ככה ובערך ככה,
מה שכתוב פה,
ו-
0, 0, 6,
ואנחנו
0,
מוצאים שבממצא
B1,
בערך,
B2,
שווה.
אבל אי
שווה
אפשר,
0, נכון?
ברוב המערכות אי אפשר לטפל בהכל.
אוקיי.
ואני צריכה ש-B1 יהיה חייב להיות 0.
וזה עניין כזה שאני חושב
לא,
שלכל
B1
אחד
מה
יש
שהוא
את
רוצה.
לא, אבל בשני.
נכון. B1 צריך להיות 0.
אז 0 זה
כן. אז יש לך רק וקטור אחד, רק מימד אחד פה, בגלל זה רק יש לך פה את ה-6 הזה. יש לך רק וקטור אחד, הוא מימד אחד, אז זה לא, אין לך שני וקטורים.
זה מדויק, זה
אז מתי יש לי שניים?
אם זה היה פה 0,
ראיתי רק דוגמאות של אחד.
לא, אם זה היה פה 0, שווה לך 2.
לא, אני מבינה מה אתה
שווה לך שני וקטורים. תחשבי בבסיס שם אלו קצת, וזה לא משנה, אם את רוצה שהג'ורדן הרגיל יהיה 3 ו-3.
סבבה, בסדר.
זה ג'ורדן?
זה המקורי.
אבל אז הפולינום
תחום
שלי לא היה
מתפתח לפני שהם מחשבים
הפולינום
וזה
שלי היה
גם...
זה לא דרך הייתה, אבל בבסיס היא הייתה ככה.
לא, האמת שגם סימולציה
זהו בבסיס, אז יש לך שני וקטורים, יש לך וקטור 1, 0, וקטור 0, 1.
אני לא מצאתי
אם אתה טועה גם, סימולציה אמרה לך
אבל
יכולה
יש
לעשות
כאלה.
גם בקוד, ואתה לא עדיין
זה רק מעבר
במערכת.
בסיסים.
באמת, כאילו.
אבל פה יש לך חסמים.
נכון.
לא משנה.
אם היה לי פה 3,
אז זה משלים, בדיוק, זה העניין.
אוקיי? אז
כן, אבל
כאילו
זה לא
היה...
מספיק,
אבל גם היה את
כאילו,
הלימוד.
אז עשינו הרוב בסימולציה. כאילו, עשינו גם.
אז
גם,
עכשיו היה לך
פיתחנו
וקטור 0T, או 0
אנליזה.
1 היה בסיס.
כן, זה כמו שאנחנו הבנו.
כן.
טוב, אז זה פשוט יצא לי, אני לא צריכה פה לדעת משהו.
כמעט לא...
אתה צריכה פשוט, לא, צריכה עוד כמה וקטורים.
אפשר עוד משהו קטן? כאילו, יש להם הרבה דברים, אבל ספציפית זה משהו שציירת היום.
Is there a retake on this exam? Do you have any clue when it will be?
No. It depends how many people will take it and then they will start.
So it would still be this semester or even...
It will be during the summer.
Okay.
Like, I don't know. It requires that I grade the exams and then people will get grades. It will be at least...
So if the retake, regardless, what happens in the first exam? כאילו בכל מקרה יש מועד? לא הבנתי.
אני חושב ש... No, if at least one person wants the best, then we will get.
Because we need stuff to you.
What?
We'll talk to you later. Well,
Yeah, and I think...
בסדר, תהיה לך הוכחה.
I think also because they said about the security situation that there will be more tests anyway in all the courses. I'm not sure.
The physiology examiner was waiting for the silence. I was waiting when I read Shaul's question. I was so waiting. לגבי הציור הזה שציירנו היום.
כן.
זה אומר הכחול, זה אומר שזה אגן המשיכה שלנו. יש כאילו כל מה שמתחיל פה הולך לשם, כל מה שמתחיל פה הולך לכאן.
זה, פיתחתי את זה בתור משהו שיכול לסייע לך להסביר את התיאור המילולי. זה קצת... צריך להכיר את המושג של בייס מוניפקשן. כנראה שאני...